Hi guys, this is Michael J. Vargas and I would like to present to you the QMS principle number 4 for process approach, which is the failure mode and effect analysis. What is FMEA? It is an engineering analysis done by a cross-functional team of subject matter experts that thoroughly analyzes product design or manufacturing processes early in the product development process. Its objective is finding and correcting weaknesses before the product gets into the hands of the customer. It is a step-by-step approach for collecting knowledge about possible points of failure in a design, manufacturing process, product, or service. So, giving you the brief history of FMEA. FMEA was formalized in 1949 by the U.S. Armed Forces by the introduction of MAIL-P1629 procedure for performing a failure mode effect and criticality analysis. The objective was to classify failures according to their impact on mission success and personal equipment safety. It was later adopted in the Apollo space program to mitigate risk due to small sample sizes. The use of FMEA gained momentum during the 1960s with the push to put a man on the moon and return him safely to Earth. In the late 1970s, the Ford Motor Company introduced FMEA to the automotive industry for safety and regulatory consideration after the Pinto affair. They also used it to improve production and design. In the 1980s, the automotive industry began implementing FMEA by standardizing the structure and methods through the Automotive Industry Action Group. Although developed by the military, the FMEA method is now extensively used in a variety of industries including semiconductor processing, food service, plastics, software, aeronautics, automotive, and healthcare. So, why do FMEA? There are a number of business reasons to implement an effective FMEA process. When done well, FMEA is a proven tool to reduce life cycle warranty costs. When done well, FMEA will reduce the number of oops during product development. It is far less expensive to prevent problems early in product development than fix problems after launch. FMEA can identify and address safety issues before a potential catastrophe. So, what are the purposes of FMEA? To identify and fully understand potential failure modes and their causes, and the effects of a failure on the system or end users for a given product or process. To assess the risks associated with identified failure modes, effects, and causes, and prioritize issues for corrective action. To identify and carry out corrective actions to address the most serious concerns. So, what are the type of FMEA? System FMEA. It is the highest level analysis of an entire system, made up of various subsystems. The focus is on system-related deficiencies, including system safety, system integration, interfaces, or interaction between subsystems or with other systems, interactions with the surrounding environment, human interactions, service, and other issues that could cause the overall system not to work as intended. Design FMEA. The focus on the product design, typically at the subsystem or component level. The focus is on design-related deficiencies, with emphasis on improving the design and ensuring product operation is safe and reliable during the useful life of the equipment. The process FMEA. It focuses on the manufacturing or assembly process, emphasizing how the manufacturing process can be improved to ensure that a product is built to design requirements in a safe manner with minimal downtime, scrap, and rework. So the scope of a process FMEA can include manufacturing and assembly operations, shipping, incoming parts, transporting of materials, storage, conveyors, tool maintenance, and labeling. Process FMEA most often assume that design is sound. What are the FMEA success factors? There are 6 broad success factors that are critical to uniformity of success in the application of FMEA in any company. Number 1 is the understanding the fundamentals and procedures of FMEA, including the concepts and definition. Selecting the right FMEA projects. Preparation steps for each FMEA project. applying lessons learned and quality objectives, providing excellent facilitation, implementing an effective company-wide FMEA process. Implementing these FMEA success factors will help ensure FMEA achieve safe, reliable, and economical products and processes. So, understanding the fundamentals and procedures of FMEA. It is important to begin with an understanding of the basic definitions of FMEA. Time spent toward understanding the fundamental concepts and definition of FMEA will shorten the time in meetings and help ensure high-quality results. There is no substitute for having a thorough knowledge and understanding of the FMEA definitions and concepts. So, Figure 1 is an example of a generic FMEA worksheet truncated after the recommended actions column. The numbers in the illustration corresponds to the subsections in this paper. The definitions are presented in the sequence they are normally developed in the FMEA project. Understanding the fundamentals and procedures of FMEA. Number 1 is the item. It is the focus of the FMEA project. For a system FMEA, this is the system itself. For a design FMEA, this is the subsystem or component under analysis. For a process FMEA, this is usually one of the specific steps of the manufacturing or assembly process under analysis, as represented by an operation description. So, Figure 2 is an example of an item for a design FMEA, and Figure 3 is an example of an item for a process FMEA. For the number 2, its function. It is what the item or process is intended to do, usually to a given standard or performance or requirement. For design FMEA, this is the primary purpose or design intent of the item. For the process FMEA, this is the primary purpose of the manufacturing or assembly operation. Functions are typically described in a verb-noun format. It is essential to include the standard or performance as part of the function statement in order to help describe the failure mode. There can be many functions for each item or operation. So, Figure 4 is an example of function for a design FMEA. Figure 5 is an example of function for a process FMEA. Note that in the case of process FMEA, the function can be similar to the item, as described in the operation description for the manufacturing or assembly process. Number 3 is the failure mode. It is the manner in which the item or operation potentially fails to meet or deliver the intended function and associated requirements. It may include failure to perform a function within defined limits, inadequate or poor performance of the function, intermittent performance of a function, and or performing an unintended or undesired function. So, Figure 6 is an example of failure mode for a design FMEA. Figure 7 is an example of failure mode for a process FMEA. Number 4 is the effect. It is the consequence of the failure on the system or end user. This can be a single description of the effect on the top-level system or end user, or 3 levels of effects like local, next higher level, and end effect. For process FMEA, consider the effect at the manufacturing or assembly level as well as at the system or end user. There can be more than one effect for each failure mode. However, typically, the FMEA team will use the most serious of the end effects for the analysis. Figure 8 is an example of effect for a design FMEA. Figure 9 is an example of an effect for a process FMEA. Number 5 is the severity. Severity is a ranking number associated with the most serious effect for a given failure mode, based on the criteria from a severity scale. It is a relative ranking within the scope of the specific FMEA determined without regard to the likelihood or occurrence or detection. Figure 10 is an example of severity scale for design FMEA. Figure 11 is an example of severity scale for process FMEA. Number 6 is the cause. It is the specific reason for the failure, preferably found by asking why until the root cause is determined. For design FMEA, the cause is the design deficiency that results in the failure mode. For process FMEA, the cause is the manufacturing or assembly deficiency that results in the failure mode. So figure 12 is an example of cause for design FMEA, and the next figure is the example of cause for process FMEA. Number 7 is the occurrence. It is a ranking number associated with the likelihood that the failure mode and its associated cause will be present in the item being analyzed. For system and design FMEA, consider the likelihood of occurrence during the design life of the product. For process FMEA, consider the likelihood of occurrence during production. It is based on the criteria from the corresponding occurrence scale and has a relative meaning rather than absolute value, determined without regard to the severity or likelihood of the detection. Figure 14 is an example of occurrence scale for design FMEA. Figure 15 is an example of occurrence scale for process FMEA. Number 8, controls. These are the methods or actions currently planned or already in place to reduce or eliminate the risk associated with each potential cause. Controls can be the methods to prevent or detect the cause during product development, or actions to detect a problem during a service before it becomes catastrophic. There can be many controls for each cause. For system or design FMEA, prevention type design controls describe how a cause, failure mode, or effect in the product design is prevented based on current or planned actions. They are intended to reduce the likelihood that the problem will occur and are used as input to the occurrence ranking. Only those prevention type controls that are currently planned or already in place should be entered onto the FMEA worksheet. Figure 16 is an example of design controls for design FMEA. For process FMEA, prevention type process controls describe how a cause, failure mode, or effect in the manufacturing or assembly process is prevented. Based on current or planned actions, detection type process controls describe how a failure mode or cause in the manufacturing or assembly process is detected. Based on current or planned action, before the item is shipped for the manufacturing or assembly plant, and are used as an input to the detection ranking. Figure 17 is an example of process control for process FMEA. Number 9 is the detection. It is a ranking number associated with the best control from the list of detection type controls. Based on the criteria from the detection scale, it considers the likelihood of detection of the failure mode cause according to the defined criteria. It is a relative ranking within the scope of the likelihood of occurrence. Figure 18 is an example of detection scale for design FMEA, and figure 19 is an example of a detection scale for process FMEA. Number 10 is the risk priority number, or RPM. It is a number ranking of the risk of each potential failure mode or cause made up of the arithmetic product of the three elements: severity of the effect, likelihood of occurrence of the cause, and likelihood of detection of the cause. So the formula for RPM is equal to severity multiplied by occurrence and multiplied to detection. So number 11 is the recommended actions. Tasks recommended by the FMEA team to reduce or eliminate the risk associated with potential causes of failure. They should consider existing controls, relative importance of the issue, and the cost of effectiveness of the corrective action. There can be many recommended actions for each cause. In practice, it usually takes more than one, and sometimes many actions to address high-risk issues. And that ends my presentations. Please check these references if you want to learn more about FMEA. Thank you guys for watching. I hope you learned something from me. Thank you.